The Fibonacci sequence is one of the most fascinating patterns in mathematics. It's defined as a sequence where each number is the sum of the two preceding ones. The sequence typically starts with 0 and 1. The sequence then continues with 1, 2, 3, 5, 8, 13, 21, 34, and so on. Each number in the sequence is calculated by adding the two previous numbers. For example, 1 plus 2 equals 3. Then the next number is calculated by adding 2 plus 3, which equals 5. The sequence was first described by Italian mathematician Leonardo of Pisa, known as Fibonacci, in the 13th century. He introduced it in his book Liber Abaci, published in 1202, where he used it to model rabbit population growth. A fascinating property emerges when we look at the ratio between consecutive Fibonacci numbers. As the sequence progresses, dividing each number by its predecessor approaches a specific value. This value is known as the golden ratio, phi, approximately equal to 1.618. This mathematical pattern appears throughout the natural world, suggesting it may represent an optimal arrangement for growth and efficiency. Now let's explore how this pattern manifests in plant growth. Plants exhibit Fibonacci patterns in truly remarkable ways. The spiral arrangement of leaves around a stem, known as phyllotaxis, often follows the Fibonacci sequence. This arrangement is based on the golden angle of approximately 137.5 degrees, which ensures each leaf receives maximum sunlight without being blocked by leaves above. As new leaves grow, they position themselves at this golden angle from the previous leaf, creating the optimal spacing. The number of petals on flowers frequently matches Fibonacci numbers, such as 3, 5, 8, 13, and 21. This pattern appears across diverse plant families. Lilies and irises often have 3 petals, buttercups have 5, delphiniums have 8, and many daisies have either 13, 21, or 34 petals. Some of the most striking Fibonacci patterns appear in plant spirals, such as pine cones, pineapples, and sunflower heads. In these structures, spirals form in both clockwise and counterclockwise directions. Amazingly, the number of spirals in each direction are adjacent Fibonacci numbers. These Fibonacci patterns provide important evolutionary advantages to plants. They optimize space utilization, allowing plants to pack structures efficiently. They enhance structural integrity, especially in developing buds and seed heads. They maximize resource collection like sunlight and water, and they help plants adapt to various environmental pressures. These plant patterns are just one example of how the Fibonacci sequence appears in nature. Next, we'll explore how Fibonacci numbers also manifest in animal structures. The Fibonacci sequence appears throughout animal structures and populations in remarkable ways. Nautilus shells grow in a logarithmic spiral that approximates the golden ratio. This special ratio of approximately 1.618 allows the shell to maintain its shape while increasing in size. Honeybees' family trees follow the Fibonacci sequence in a fascinating way. A male bee has only one parent, a female, while a female bee has 2 parents, one male and one female. This creates a Fibonacci pattern in ancestry counting. Going back generations, we get 1, 2, 3, 5, 8, and so on, following the Fibonacci sequence perfectly. The rabbit population growth problem is actually the original example Fibonacci used to illustrate his sequence in 1202. In his example, rabbits mature in 1 month and then produce a new pair each month. With these assumptions, the population follows the Fibonacci sequence exactly. The Fibonacci sequence is also evident in other animal structures. Falcons often fly in spiral patterns that follow logarithmic curves based on the golden ratio, optimizing their hunting efficiency. The horns of animals like rams and sheep curl in spirals that closely match the golden ratio, balancing growth with structural stability. These examples demonstrate how the Fibonacci sequence is ingrained in animal structures and populations throughout nature. The prevalence of Fibonacci patterns in nature can be explained through physics and evolution. From a physical perspective, Fibonacci patterns represent efficient solutions to packing problems, how to arrange structures in limited space with minimal energy expenditure. The golden ratio, which appears throughout Fibonacci structures, provides an optimal balance between growth and structural stability. From an evolutionary perspective, these patterns emerged because they confer survival advantages. Plants with Fibonacci-based leaf arrangements can capture more sunlight without self-shading. Spiral structures provide strength with minimal material. This is why we see these patterns in shells, horns, and other biological structures that need to withstand physical forces. These patterns weren't designed, but evolved independently across vastly different species. This convergent evolution happened because Fibonacci patterns represent optimal solutions to common biological challenges. In summary, Fibonacci patterns appear in nature because they represent physically efficient arrangements that provide evolutionary advantages. These mathematical patterns weren't designed by nature, but rather emerged through natural selection as optimal solutions to common challenges faced by living organisms. Fibonacci patterns extend well beyond living organisms into other natural systems. In weather patterns, the spiral formations of hurricanes often approximate the golden ratio. River networks display fractal branching patterns that follow mathematical principles similar to the Fibonacci sequence. At the microscopic level, certain crystal growth patterns exhibit Fibonacci-like organization. DNA molecule arrangements also show proportions related to Fibonacci mathematics, with base pair spacing often following golden ratio principles. These widespread occurrences suggest the Fibonacci sequence represents a fundamental principle of efficient natural organization. Understanding these patterns helps scientists develop biomimetic technologies that apply nature's mathematical efficiency to human engineering challenges. By studying how Fibonacci patterns create efficiency in natural systems, we can design better technologies that harmonize with nature's mathematical principles.